Welcome to No Human Left Behind, AI the podcast. In today's episode, a conversation on computer vision, empowering machines to see.
Welcome to the deep dive. Today we're going to be diving deep into the world of computer vision,
That's right.
giving machines the power to see
Yeah.
like we do. For this deep dive, we've got some excerpts from a fascinating Intro to AI course.
Yeah.
And we're going to break down the fundamentals of computer vision, whether you're prepping for that big tech meeting or just curious about how machines are learning to perceive the world around us. So
It's a really cool topic.
yeah, it is. It's really cool.
It's
And it draws on so many different fields too.
Oh yeah.
Yeah, it's really interdisciplinary. So computer science, obviously, math, engineering,
Yeah.
even cognitive science.
Really.
Yeah, so it's really like we're trying to take the secrets of our own visual system
Wow.
and replicate that in machines.
That's what I find so cool about computer vision. It's not just science fiction anymore.
Yeah,
It's self-driving cars,
that's right.
medical diagnoses, facial recognition.
It's already woven into our lives. But before we get ahead of ourselves,
Yeah.
let's take a step back.
Sure.
What exactly is computer vision?
At its core, computer vision is about giving computers the ability to extract meaningful information from images and videos.
Okay,
So it's not just about identifying what's there,
right.
but understanding the relationships between objects, the context of a scene, and ultimately
Yeah.
deriving insights that even humans might miss.
So it's not just about seeing.
No.
It's about understanding
That's right.
what you see,
Okay.
okay? And that journey starts with the image itself, right?
Uh-huh.
How do we go from light
Yeah.
to something a computer can actually work with?
It's a fascinating process. Light reflects off of a scene. A camera lens focuses that light,
Right.
and then a sensor converts the light intensity into electrical signals,
Okay.
which are then digitized into those tiny building blocks we call pixels.
Ah, pixels.
Yeah.
So is it as simple as more pixels, better image?
Well, that's spatial resolution.
Okay.
And yes, generally higher resolution means a sharper image,
Right.
but there's also bit depth,
Okay.
which determines the range of colors or intensities a pixel can represent.
Okay.
So think of it like the richness of color.
So a high-resolution image with good bit depth
Yes.
would be like looking at a super detailed, vibrant painting.
That's a great analogy.
Okay, great. And most of us are familiar with the RGB color model.
Right.
Red, green, and blue light combining to create all the colors we see.
Uh-huh.
But there are other models too, right?
Yes, there are.
Like
HSV,
HSV.
hue, saturation value,
Okay,
which can be more useful for certain tasks.
I see.
It's like choosing the right tool for the job.
Right.
You wouldn't use a hammer
Yeah.
to screw in a screw.
Oh, yeah, okay, that makes sense.
Yeah.
But having all those pixels is just the beginning.
Right.
Then we have to teach computers to actually do something
Uh-huh.
with that information. How do they start picking out what's important in an image?
That's where feature detection and extraction come in.
Okay.
It's like teaching a computer to find the most informative clues
Uh-huh.
in a visual scene.
Okay.
We're talking corners, edges, textures.
I see.
These are the unique points or regions
Okay.
that help distinguish one object from another.
So instead of trying to analyze every single pixel,
Yeah.
the computer is focusing on those key features
Uh-huh.
that act like landmarks.
Precisely.
Yeah.
And there are different algorithms designed for this.
Okay.
Some, like the classic Harris corner detection, are great at finding those sharp points where the image gradient changes rapidly.
Gradients.
Yeah.
That's like how much the color changes over a certain area, right?
Exactly.
Okay.
And then we have more advanced algorithms like SIFT and SRF.
Okay.
They're not just looking for simple corners, but complex patterns and textures
Okay.
that are
Yeah.
invariant to changes in scale, rotation, or lighting.
So even if the object is farther away, rotate,
Yeah.
or the lighting is different,
Uh-huh.
these algorithms can still identify those consistent features.
Yes.
That's pretty impressive.
It is. And think about the properties we discussed earlier. These algorithms are designed to find features that are repeatable.
Okay.
So you find them consistently.
Right.
Distinctive, meaning they're different from other features, and invariant to those transformations.
Okay, so we've got this clean image.
Yeah.
We've identified these key features.
Yeah.
But now comes the truly mind-blowing part, right?
Yes.
Actually recognizing what the computer is seeing. Like, is that a cat, a car, or a cloud?
You're talking about object recognition and classification,
Okay.
which is where we move from simply seeing to understanding.
Right.
Early methods like template matching were limited.
Okay.
Because they relied on comparing the image to predefined outlines of objects.
But real-world objects come in so many variations.
Exactly.
A cat can be sitting, stretching, sleeping. There's no one-size-fits-all outline.
Exactly. That's where feature-based methods came in.
Okay.
Remember those SIF, T, and SRF features we discussed?
Uh-huh.
Those became the foundation for training machine learning models.
Okay.
To recognize objects based on those unique descriptive features.
I see.
Rather than rigid outlines.
So instead of a simple outline of a cat,
yeah,
we're feeding the computer a whole set of clues about what makes a cat a cat?
That's a great way to put it.
Okay, good.
But then came the revolution. Deep learning.
Yeah.
Specifically convolutional neural networks, or CNNs.
CNNs.
Which took object recognition to a whole new level.
CNNs, they're kind of the rock stars of deep learning these days.
Absolutely.
Yeah.
What's fascinating about them is they learn directly from the pixel data.
Okay.
Finding those intricate patterns and hierarchies of features.
Really?
That humans might not even be consciously aware of.
So instead of us telling the computer what features to look for.
That's right.
It's figuring it out on its own based on massive amounts of data.
Precisely.
Yeah.
And it's achieving incredible accuracy.
Really?
Yeah. The ImageNet dataset, which contains millions of labeled images, has been a proving ground for CNNs. And the results have been astounding.
So these CNNs are training on a massive scale.
Yeah.
Getting better and better at identifying objects. But I'm guessing there are still challenges.
Of course. The real world is messy and unpredictable. Variations in lighting, viewpoints, the things blocking the view.
Right.
These can all trip up even the most sophisticated algorithms.
Right. And then there's the challenge of distinguishing between very similar objects.
Yes.
Like telling apart different breeds of dogs.
Right.
It's like the computer needs to become a connoisseur of canine features.
That's a great analogy.
Okay, good. Fine-grained classification is a tough nut to crack.
Yeah.
But it's an area where we're seeing a lot of progress.
It is.
It's amazing how much computer vision has advanced in just a few years.
Yeah, it is, yeah.
But let's not forget, recognizing objects is just one piece of the puzzle.
Right.
What about understanding how those objects relate to each other?
Yeah.
That's where image segmentation comes in, right?
You got it.
Okay.
Image segmentation is like taking object recognition a step further.
Okay.
Instead of just saying, there's a cat, the computer is outlining the cat's exact shape.
Wow.
Separating it from the background.
Okay.
Creating a pixel-by-pixel map of what belongs to each object in the scene.
So it's like drawing those invisible boundaries that our brains do effortly, but making it explicit for the computer.
Exactly. And there are different techniques for this.
Okay.
Some simpler, like thresholding, where you essentially pick a cutoff point for pixel values.
Okay.
And others more complex, like region-based methods that group similar pixels together based on color, texture, or intensity.
It sounds like there's a whole world of algorithms.
There is.
Working behind the scenes to create these segmentation maps.
There really is. And again, deep learning has been a game changer here.
Yeah.
Fully convolutional networks, or FCNs, are especially good at this task, producing those detailed segmentation maps.
FCNs. Yet another deep learning superstar?
They are.
I'm starting to see a pattern here.
Yeah.
It seems like deep learning has revolutionized almost every aspect of computer vision.
It's hard to overstate its impact.
Yeah.
And this segmentation capability isn't just a cool trick. It has real-world applications.
Right.
Think medical imaging.
Okay.
Where doctors could use it to precisely outline organs or tumors.
Wow.
Or self-driving cars, using it to distinguish the road from other objects.
Wow, that's incredible.
Oh, yeah.
So we've covered a lot of ground.
We have.
From how images are formed, this mind-blowing deep learning models that are enabling computers to recognize and segment objects. It's clear that deep learning is a major player in all of this.
Right.
But how do these deep learning models actually work? I'm ready to take a deeper dive into the world of CNNs.
Let's do it.
Okay.
CNNs, as we mentioned, are specifically designed for image data.
Okay.
They work by using these layers, called convolutional layers, to learn those spatial hierarchies of features.
Spatial hierarchies. Can you break that down for me?
Yeah. Imagine the CNN is looking at an image at different scales.
Okay.
First, it picks up basic features like edges and corners.
Right.
Then it combines those into more complex features like shapes.
Yeah.
And eventually, it can recognize entire objects based on these hierarchical patterns.
So it's like building blocks going from simple to complex layer by layer.
Exactly. And there are other layers too, like pooling layers,
Okay.
which help reduce the amount of data and make the model more efficient
Right.
without losing those crucial features.
Efficiency is always a good thing.
Yeah,
Especially when you're dealing with millions of pixels.
it is.
But ultimately, we need the CNN to make a decision.
That's right.
Right. Like, this is a cat. Yeah.
Or this is a car.
Right. And that's where fully connected layers come in.
Yeah, okay.
They take those learned features from the previous layers and essentially act like a voting system,
Okay.
weighing the evidence and outputting a final classification or prediction.
So it's like a relay race,
Mm-hmm.
each layer passing the baton to the next. And finally, we get the answer. And I've heard there are different types of CNN architectures,
Yes, there are.
each with its own strength.
Yeah,
Can you tell me about some of the big names?
absolutely. We have AlexNet,
Okay.
which was an early champion,
Right.
showing the world just how powerful deep learning could be for image classification.
Okay.
Then there's VGG,
Uh-huh.
known for its deep networks with smaller convolutional filters,
Okay.
allowing it to learn more intricate features.
Okay.
And of course, ResNet,
Resin.
which introduced a groundbreaking concept called residual connection.
Residual connections, what's so special about them?
Think of them as shortcuts within the network.
They allow information to flow more easily across layers,
Right.
which was a game changer for building even deeper networks.
Right.
Before ResNet, as networks got deeper, they actually started performing worse.
Really?
Yeah, due to something called the vanishing gradient problem.
Interesting. So ResNet solved this vanishing gradient problem
It did.
and allowed us to build deeper, more powerful CNNs.
Exactly. Deeper networks can learn more complex patterns,
Right.
leading to better accuracy.
Makes sense.
And we can't forget Inception,
Okay.
which introduced the concept of multi-scale processing,
I see.
allowing the network to look at the image at different resolutions simultaneously.
So instead of just looking at the big picture,
Yeah.
Inception is also paying attention to the finer details.
Precisely.
Okay.
And all of these innovations have pushed the boundaries of what's possible with computer vision.
Wow.
We've only scratched the surface
Yeah.
of what these models can do.
This is all incredibly fascinating.
Yeah.
It feels like we've opened up a whole new world of possibilities with CNNs.
We have.
But we've been focusing on still images so far.
Right.
What about videos? Capturing movement and the flow of time.
Yeah.
Seems like a whole other challenge.
It is.
What's the state of the art in video analysis?
That's a great question.
Yeah.
And you're right.
Uh-huh.
Video is a whole other beast.
Yeah.
We're not just dealing with individual images,
Right.
but sequences of them
Okay.
with movement and time to consider.
Yeah.
It's like teaching a computer to understand a story
Oh.
unfolding before its eyes.
So it's not just about what's in the image, but also what's happening over time.
Exactly.
Okay.
So are CNNs still the go-to solution here?
Yeah. Are they?
They're definitely part of the equation, but we also have other powerful tools at our disposal.
Okay.
Recurrent neural networks, or RNNs,
Okay.
are specifically designed to handle temporal dependencies,
I see.
understanding how things change over time.
So if a CNN is like a snapshot, an RNN is like a movie, capturing the flow of events.
That's a great way to think about it.
Okay, great. And a specific type of RNN called LSTM,
Yes.
long short-term memory,
Yeah.
has been very successful in video analysis tasks,
Yes.
like action recognition. Action recognition. So the computer's trying to figure out if someone is running, jumping.
Yeah, exactly.
Okay.
It's analyzing those subtle changes in pose and motion over time to identify the action being performed.
That sounds incredibly complex.
It can be.
And what about those 3D convolutional neural networks, or 3D CNNs?
Yeah.
You mentioned them earlier.
They're specifically designed to capture both spatial and temporal information from videos.
Okay.
Think of them as a hybrid between CNNs and RNNs,
Mm-hmm.
able to see the content of each frame and how things are moving from frame to frame.
So they're looking at both the what and the how of the video.
Precisely.
Okay.
And this has led to some really cool applications,
Oh.
like surveillance systems that can automatically detect suspicious activity,
I see.
sports analysis tools that track player movements,
Wow.
and even systems that can recognize gestures in human-computer interaction.
That's incredible.
It is.
It's like we're giving computers the ability to not just see, but also understand the flow of events in the world.
Uh-huh.
But with all this progress, I'm guessing there are still challenges that need to be addressed.
Of course.
Even with deep learning, computer vision isn't perfect, right?
You're absolutely right. There are definitely limitations in areas where more research is needed.
Okay.
For one thing, deep learning models are incredibly data hungry.
Right.
They need massive amounts of labeled data to train effectively.
Yeah.
Which can be very costly and time-consuming to create.
So even with all this amazing technology, we're still limited by the amount of data we can feed these models.
In a way, yes.
Okay.
And then there's the problem of those adversarial examples we touched on earlier.
Right.
Those specially crafted inputs designed to fool the model.
Like tricking a self-driving car into thinking a stop sign is actually a speed limit sign.
Exactly.
That's scary.
It's a serious concern.
Yeah.
It highlights the vulnerability of these models and reminds us that there's still work to be done.
Right.
To make them more robust.
It's a reminder that these systems, while powerful, are still under development.
Right.
And we need to approach them with a healthy dose of caution.
Yes.
But that doesn't take away from the incredible progress that's been made.
Of course not.
It feels like computer vision is on the cusp of a whole new era of innovation.
Absolutely.
Okay.
We're moving beyond just recognizing objects to truly understanding the visual world.
Right.
And that opens up endless possibilities.
Yeah.
But we also need to be mindful of the implications of this technology as it becomes more powerful and pervasive.
That's a great point.
Yeah.
And it leads us perfectly into the next part of our deep dive, where we'll explore the ethical considerations and challenges that come with this rapidly advancing field.
Right.
But first, we'll take a short break.
Okay.
Stay tuned.
That's good.
Welcome back to the deep dive. We've spent the first part of our journey exploring the nuts and bolts of computer vision. You know how it works.
Right.
The algorithms involve the power of deep learning.
Yes.
We've seen how machines are learning to see the world.
Right.
Identifying objects, even understanding scenes in ways that were once thought impossible.
Yeah, it really is amazing.
It's truly mind-blowing. But what I find even more exciting is seeing how this technology is moving beyond the lab and into the real world, transforming entire industries.
Absolutely. The applications of computer vision are exploding across various fields.
Yeah.
It's not just a future possibility anymore.
Right.
It's actively shaping our present.
Let's start with healthcare. I've heard so much about how computer vision is revolutionizing medical diagnoses and treatments.
Yes.
Can you give us a glimpse into what's happening there?
Imagine a world where diseases can be detected earlier and more accurately than ever before.
Okay.
That's the promise of computer vision in healthcare.
Right.
Take medical imaging, for example.
Okay.
Radiologists spend countless hours analyzing X-rays, CT scans, MRIs.
It's like trying to find a needle in a haystack sometimes, right?
Yeah.
Especially those subtle signs of disease that might be easily missed by the human eye.
Exactly.
Yeah.
And that's where computer vision comes in.
Okay.
These algorithms can be trained to spot those subtle anomalies.
Right.
Those tiny variations that might indicate the presence of a tumor, a fracture, or even a developing heart condition.
So it's like having a superpowered assistant working alongside doctors.
Yeah.
Helping them see things they might otherwise miss.
That's a great way to put it.
Okay, good.
And it's not just about detection.
Right.
Computer vision can also assist with diagnosis.
Okay.
Helping doctors determine the specific type and severity of a disease. It can even guide treatment planning.
Okay.
Ensuring that patients receive the most effective and personalized care possible.
That's incredible. It's like computer vision is giving doctors a whole new set of tools to improve patient outcomes. Are there any specific examples of how this is being used in practice?
Absolutely. One area where it's making a huge impact is in cancer detection.
Okay.
Algorithms are being trained to analyze mammograms and identify early signs of breast cancer, potentially saving countless lives through early intervention.
That's powerful. It's like giving women a fighting chance against this devastating disease. Are there other areas where computer vision is making a difference in healthcare?
Definitely. It's being used in ophthalmology to detect diabetic retinopathy, a leading cause of blindness. By analyzing images of the retina, these algorithms can identify signs of damage and alert doctors to the need for treatment.
It's amazing how computer vision is improving healthcare across so many specialties.
It is.
What about other fields? Where else are we seeing this technology making a real-world impact?
Well, transportation is another area where computer vision is driving innovation.
Okay.
And I'm not just talking about self-driving cars.
Okay.
Although that's certainly a big one.
Okay. Let's talk self-driving cars.
Okay.
It's one of those futuristic technologies that's quickly becoming a reality.
It is.
How is computer vision playing a role in making this happen?
It's the core technology that allows self-driving cars to perceive and navigate the world around them.
Okay.
These cars are equipped with an array of cameras and sensors, constantly gathering visual data, which is then processed by sophisticated computer vision algorithms.
So the car is essentially seeing its surroundings, the road, other cars, pedestrians, traffic signals, all those things a human driver needs to be aware of.
Exactly.
Okay.
It's building a real-time understanding of the driving environment, identifying obstacles, predicting potential hazards, and making split-second decisions to ensure the safety of everyone on the road.
That's a lot of responsibility.
It is.
It's incredible to think how far we've come in developing this technology.
Yeah.
But I imagine there are still challenges, right?
Of course. Self-driving cars operate in a complex and dynamic world.
Sure.
And there are still scenarios that can trip them up.
Right.
Unpredictable weather conditions, unexpected obstacles, the nuances of human behavior.
It's like that saying, humans are the hardest variable to control.
Exactly.
Okay.
And that's why ongoing research and development are crucial.
All right.
We need to constantly refine these algorithms, train them on massive data sets, and expose them to as many real-world scenarios as possible.
It sounds like self-driving cars are still very much a work in progress.
They are, yeah.
But even so, the potential benefits are immense.
They are.
Imagine a world with fewer accidents, reduced traffic congestion,
and increased mobility for people who are currently unable to drive themselves.
Right.
It's a future worth striving for.
Yeah.
And computer vision will be the driving force behind making it a reality.
Absolutely. But computer vision's impact on transportation goes beyond just self-driving cars.
Right.
It's also being used to improve traffic flow management, optimize public transportation systems, and even inspect infrastructure for safety and maintenance.
You're right. It's like computer vision is becoming the eyes and ears of our transportation networks, making them safer, more efficient, and more accessible for everyone.
It's amazing to see how this technology is being applied in such practical and impactful ways.
It is, yeah.
But let's not forget about the fun stuff.
Yeah.
I've heard that computer vision is also making waves in the world of entertainment.
Absolutely.
Okay.
And you're not just talking about those cool AR filters on social media.
Right.
Although those are definitely a fun application.
Yeah.
Computer vision is at the heart of some of the most immersive and engaging entertainment experiences today.
Like those incredible special effects we see in movies these days.
Yes.
I can only imagine the amount of work that goes into bringing those fantastical creatures and epic battle scenes to life.
It's a massive undertaking.
Yeah.
And computer vision plays a crucial role in making it happen.
Right.
Think about motion capture.
Okay.
Where an actor's movements are tracked and used to animate digital characters. That's all thanks to computer vision.
So it's like a digital puppet master.
Yeah.
Bringing those imaginary worlds to life. What other tricks does computer vision have up its sleeve when it comes to entertainment?
Well, how about this? Personalized entertainment experiences.
Okay.
Tailored to your individual preferences.
Oh, wow.
Computer vision algorithms can analyze your viewing history.
Right.
Understand what you like and dislike. And recommend movies, TV shows, even video games that are most likely to appeal to you.
So it's like having a personal entertainment concierge.
Yeah.
No more endless scrolling through streaming services.
Right.
Trying to find something to watch.
Exactly.
Good.
And it goes beyond just recommendations.
Okay.
Computer vision is also being used to create interactive games that respond to your movements and gestures.
Right.
It's blurring the lines between the real and virtual worlds, creating truly immersive experiences.
Like those dance games where you have to follow the moves on the screen?
Exactly.
Yeah.
Or imagine playing a virtual reality game where your every move is tracked and translated into the game world.
Right.
Computer vision makes all of that possible.
It's amazing how computer vision is not only creating the entertainment, but also helping us find it and interact with it in new and exciting ways.
It is.
But we've only just scratched the surface of the applications of this technology.
You're absolutely right. We've talked about healthcare, transportation, entertainment.
Right.
But the list goes on and on.
Right.
Manufacturing, retail, agriculture, security.
Wow.
There's hardly an industry that's not being touched by the power of computer vision.
It's like this technology is becoming ubiquitous, woven into the very fabric of our lives.
And as computer vision continues to evolve, as those algorithms get smarter and more sophisticated, we can expect even more incredible applications to emerge, impacting our lives in ways we can't even imagine yet.
It's an exciting time to be witnessing this technological revolution.
Yeah.
But with all this progress, it's also important to pause and reflect on the potential downsides.
You're right. Every powerful technology comes with its own set of challenges and limitations.
Right.
And computer vision is no exception.
Well, that's a perfect segue into the final part of our deep dive.
Okay.
We'll be exploring the challenges, limitations, and ethical considerations that we need to be aware of as computer vision becomes more pervasive in our world.
Sounds good.
Welcome back to the deep dive. We've spent the last 2 parts exploring this fascinating world of computer vision, from those, the basics of image formation, all the way to those incredible deep learning models that are allowing computers to, see and understand the world in ways that we, never really thought possible before.
Yeah, it's really incredible how far we've come.
It's truly been an incredible journey of innovation. But with any powerful technology, it's important to kind of take a step back and consider the potential downsides. What are some of the, challenges and limitations that computer vision still faces?
Well, one of the biggest hurdles we've encountered is the sheer amount of data these deep learning models require.
Yeah.
They're incredibly data hungry.
Right.
Needing massive data sets of labeled images and videos to train effectively.
We talked about this earlier, but, it bears repeating. It's not just about having a lot of data.
Right.
It's about having the right data, right?
Absolutely. Yeah.
Data that's representative of the real world.
Yes.
That captures all the variations and complexities these systems will encounter.
If the training data is biased or incomplete, the model will likely reflect those biases.
Right.
Leading to inaccurate or even harmful outcomes. It's like teaching a child with a skewed textbook.
Yeah.
They'll learn a distorted view of the world.
That's a great analogy. It really highlights the responsibility we have in ensuring that these systems are trained on data that's fair.
Yes.
Balanced and truly reflective of, the diversity of the real world.
Absolutely.
And even with carefully curated data, there are still challenges.
Right.
Current computer vision systems can be surprisingly brittle.
Yeah.
They can be fooled by subtle changes in an image that a human would easily recognize, or, encounter situations they haven't seen before and make unexpected errors.
It's like that saying, computers are good at following instructions, but not so good at thinking outside the box.
Exactly. So we still have a long way to go in developing systems that possess the kind of common sense reasoning and adaptability that humans, kind of take for granted.
Humans are very good at that.
Yeah. So while these systems can be incredibly powerful in, controlled environments, they're still vulnerable to the unpredictability of the real world.
That's why it's crucial to be mindful of their limitations.
Right.
Especially as we start integrating them into critical applications like self-driving cars or medical diagnosis.
We need to be realistic about what these systems can and cannot do.
Absolutely.
And build in appropriate safeguards to mitigate potential risks.
It's like learning to drive.
Yeah.
We wouldn't just throw a teenager behind the wheel without proper training and supervision.
Exactly. We need to approach the development and deployment of computer vision systems with the same level of caution and responsibility.
I agree.
This brings up another challenge we touched on earlier, those adversarial examples.
Yeah.
These are, specially crafted inputs designed to intentionally fool the model, causing it to make incorrect predictions.
It's like creating an optical illusion for a computer.
Right.
Something that looks perfectly normal to a human, but completely throws off the algorithm.
Right. It's a bit unsettling to think that someone could exploit these vulnerabilities to cause harm.
It's a valid concern.
Yeah.
And it highlights the need for ongoing research into making these models more robust and resistant to such attacks. It's an ongoing arms race between those developing the technology and those trying to find its weaknesses.
It's a reminder that computer vision is still a very young field.
It is.
And we're still learning about its capabilities and its limitations.
Absolutely.
Speaking of risks, there are also ethical considerations that we need to address as computer vision becomes more pervasive in our lives.
Yes.
We briefly touched on the issue of data bias.
Right.
But what are some other concerns that we need to be mindful of?
One of the biggest concerns is the potential for increased surveillance.
Right.
As computer vision gets better at recognizing faces and tracking individuals, it becomes easier to monitor people's movements and activities.
It's a bit like Big Brother watching, but with even more sophisticated tools at its disposal.
Exactly.
Yeah.
And while there are certainly legitimate uses for surveillance technology,
sure,
we need to be careful about how it's deployed and ensure that it doesn't erode individual privacy or stifle freedom of expression.
It's a delicate balance between security and liberty.
It is.
And one that we need to navigate carefully.
Absolutely.
Another concern is the potential for job displacement.
Yeah.
As computer vision automates tasks that were previously done by humans.
Right.
There's a risk that certain jobs will become obsolete.
It's a fear that often accompanies technological advancements.
Right.
And it's one that we need to take seriously.
Yeah. We need to think about how we can retrain and upskill workers for the jobs of the future and ensure that the benefits of this technology are shared equitably across society.
I agree.
It's not just about creating new technologies, it's about creating a better future for everyone.
Absolutely. And ultimately, the ethical considerations surrounding computer vision boil down to one fundamental question.
Yeah.
How do we ensure that this technology is used for good and not for harm?
It's a question that we need to grapple with as individuals, as a society, and as a global community.
It's a question that requires ongoing dialogue, thoughtful consideration, and a willingness to adapt and evolve as this technology continues to advance.
It's been an incredible journey exploring the world of computer vision with you.
It has been.
We've seen its amazing capabilities, its transformative potential,
right,
but also the challenges and ethical considerations that we need to address.
Absolutely. It's a field that's constantly pushing the boundaries of what's possible.
It really is.
And it's one that will undoubtedly continue to shape our lives in profound ways.
Thanks for joining us on this deep dive into computer vision. We hope you've come away with a deeper understanding of this incredible technology and its impact on our world. We'll see you next time for another exploration of the cutting edge of technology and its impact on our lives.